So today's problem is going to be time-based key value store. Okay, design a time-based key value data structure that can store multiple values for the same key at different timestamps and retrieve the key's value at a certain timestamp. So we'll have to implement 3 different methods. First is going to be the constructor, is just going to be called timemap, and then we need the set function, which is going to set a value at a certain key at a certain time, right? So in a hash map, we have a value, and that value is always associated with a key. So basically, each key has a single value, right? But in a time map, things are slightly different. So each key can have multiple values so long as each value has a different timestamp associated with it. And our third method is going to be called get. And get's going to be pretty straightforward. We're going to give it a key, and then we're going to give it a timestamp. So I want the value associated with this key at this time, basically, right? Now, so let's have a look at the example here so it's a little bit easier to understand. So this input is going to be the series of steps that are going to be executed. The first call is going to be tilemap, and this is just going to instantiate our tilemap. And the second thing that's going to get called is the set function. And then remember, the set function takes in a key, a value, and a timestamp, right? So we're going to be setting, the key would be Alice, the value would be happy, and then the timestamp would be 1. Okay, so Alice at t equals 1 was happy, right? Then the next thing that's going to get executed is a get call. And then we're going to be grabbing the value at key equals Alice. So that's going to be this, the key. And okay, so we do have a key called Alice. And then I want the message at time 1. Okay, so here's the message at time 1. It's happy. Which is why in the example here, when it calls get Alice 1, it's going to return happy, right? Makes sense, makes sense. And then the next call here is going to be this. We're going to call get, and then the parameters are going to be Alice and 2. So we want the value at key equals to Alice, which is the value here. And then we want it at t equals 2. Well, we only have t equals to 1, not t equals to 2. So what do? Now, there is a clause here, returns a value such that set was called previously with timestamp prev less than equal to timestamp. If there are multiple of such values, returns the value associated with the largest timestamp prev. Essentially, what it's saying is that I want the value associated with the largest possible t value that is still under the thing that I just passed in, right? So here in our get function, we have a key and a timestamp, right? And we want the largest possible t value that is still less than equal to timestamp. And in this case, timestamp is 2, right? And the largest possible t that we have that is still smaller than equal to 2 is 1. So if we had t equals 0 here, like sad, maybe she was sad at t equals 0, then we would take this instead, because this is the largest t that is still under our limit. Which is why here we return happy as well. Return happy, there is no value stored for timestamp 2, thus we return the value at timestamp 1. So I'm going to deviate a little bit from the example. What if there is an input with set Bob, he is happy, current time is like 3, right? So then we would have Bob here at t equals 3 and he's happy, right? And you can kind of see this as a hash map because we can have multiple keys. You can have multiple people with their different states. Well, I just wanted to show you that because if you notice in the example, they're all Alice. So I'm just going to pretend that that got executed here, right? So onto our next line, we're going to be executing set Alice sad 3, right? So we're going to set on the key Alice the state sad at time 3. Cool. Then we have t equals 3, and then she is sad at t equals 3. And then this time, when I call get Alice 3, it's going to return this one because this is the largest possible t that is still under our timestamp, right? Which is 3 here. So this checks out. So we return sad. And that's pretty much what a time map does. Now, the next thing that we want to think about is how are we going to model our data? We had a pretty good conceptual understanding earlier, but I think I would like to formalize this a little bit more in programming terms. I think hash map is going to be the most intuitive choice for this. So, okay, we have the hash map to store the keys. And what about the values? We have this kind of association of the time and like the value here, right? And then we want to keep these things separated from each other. So maybe like a list where each element of the list is going to be an association of the time that it was inserted and the actual value itself. Now we could just use a tuple for this. It would look like this. Now, one of the most important constraints of this problem is this last point. All the timestamps of set are strictly increasing. So why is that important? That basically means that whenever I set a new value, the timestamp that I am setting it on will always be strictly increasing. So the first time I call set and Alice is sad at time 1, the next time I call set, the time has to be greater than 1. It can be 2, it can be 3, or it can be 4 or whatever, but it has to be greater than 1. So time moves forward And because time moves forward, our timestamp can only go one way. You can think of this kind of data structure to something that's used in a logging system or something. Let's say like 6 a.m. At 52 seconds, the system logs, oh, it's like waking up, it's starting, right? Starting up. And that's pretty much the same thing here. You have the time here, and then you have the message here, right? And then maybe the key can be like the machine name, right? Machine name. And then like a minute later, it'll say booting complete. And this might be a possible real life usage of a time map where all of the timestamps are in ascending order. And what's really good about this property is that because all the timestamps are going to be increasing, when we want to do search on this array, we can use binary search, which is going to save us a lot of time. And for those of you who have completed the Coco eating bananas problem, you're going to see a lot of similarities with this question. So let's move on to the search portion of this video. So we've established what our data structure should look like. And now it's time for us to figure out how we're going to do the search. Let's say this is the hash map that we have in store. And I want to get Alice's mood at t equals, let's say 6. So because we only care about Alice's mood states, we don't care about Bob's, we want to first grab Alice's array here. So let's just copy it. So, okay, so let's begin our search. Okay, so at this point, we want to initialize low and high here, right? Just standard binary search things. We're going to calculate the mid, which is going to be the index of low plus the index of high divided by 2. So that's going to be 0 plus 3 divided by 2, like so. And that'll give us 1. And our mid is going to be here. So we're going to inspect our number here at mid, okay? We want to see whether this number is a valid candidate. What does it even mean for it to be a valid candidate? Well, if the time here is less than equal to this, then it's a valid candidate, right? It could be an answer. It might not be the best answer, but at least it is an answer. So let's ask the question, is 2 less than or equal to 6? Well, the answer is yes, right? So this is a valid candidate. So our best so far is going to be 2 and sad, right? So because we found a candidate, the next question should be, can we find a better candidate? So a better candidate would be one where the number is higher than what we got right now, right? We want a number that's higher. So let's get a little greedy and look for a time that is larger than what we had. And of course, if that number is too big, then we have to scale it down. So let's keep going. So then we need to narrow our search space. Where should our search space be narrowed to? Well, we're not going to check this again because we've already considered that as part of our answer. And like we said, since we found a valid candidate, we don't care about everything to the left of this because these are numbers that are smaller than it, right? We want to find a larger number this time. So all the larger numbers reside on this half of the array, which is why we're going to move our low pointer up here. So now we have low and high, and this is going to be our new search space. And we're going to calculate mid, and mid is going to be here, right? So it's going to be 2 plus 3 divided by 2, and that'll give us this index. And once again, we're going to inspect our number here. Have we overstepped? Have we gotten too greedy? Is 4 still less than or equal to our maximum time, which is 6? Well, luckily for us, the answer is yes. So this answer is a better answer than what we just had. So we're going to update our best. It'll be 4 and crying. So then we go again. Can we find a better answer? So we know that it's none of these, and we've tried this one already. So we need to check this, right? So we're going to move our low to mid plus 1. So our low is going to come here. Low and high are both pointing at this. And then we're going to calculate the mid, which is going to be pointing at this as well. 5 is less than or equal to 6. Yes. And then our best gets updated with 5 hungry. And we're going to try to find a better answer by moving low to mid plus 1, but low is now out of bounds, so we stop, right? So our exit condition is that if low ever gets bigger than high, then we exit, right? In other words, while low is less than equal to high, we continue, right? We continue the search. All right, so what if we have a different input then? Because we got kind of lucky here. Our input is basically a number that's bigger than everything else. So of course our answer would be this. So what if we have like a number somewhere in the middle? What if it's the number 3? And for the best, we don't have anything yet. We set low here, high here, and just looking at the list, we know that 2 sad is going to be our best answer, but the computer doesn't know that yet. So we're going to start it out with mid here, right? We're going to check whether mid is a valid candidate. Well, lucky for us, 2 is less than equal to 3, so this is our current best result. So of course we're going to get greedy. We're going to move low up here as usual. Then we'll check this again. Is 4 less than or equal to 3? Well, it's not. This condition no longer holds. 4 is greater than the time limit. So this is not a valid candidate. We've gone too far. We've gotten too greedy. So because of that, we have to reduce our search space. So our answer must lie in the left half, right? So we have to move high down to here. And low and high have crossed over. Low is no longer less than equal to high. So this means that our search space is actually 0 elements. And this is going to be our best answer. Too sad. So now we know everything. All we got to do is just translate this into some code. So let's create our internal hash map first, which is just going to have a default value of a list. And in the next step, we're going to define our set function. All it's going to do is that every time set is called, because we know that the timestamps are in strictly ascending order, we're just going to append a tuple of timestamp and value to the associated key. And in our get function, we need to first get the array associated with a key, and we have to keep track of our best candidate. Well, it doesn't exist. So the time is -1, and I'm just going to put none here. So because the list is going to be sorted, we're going to use binary search. We'll set the values of low and high. We're going to write our while loop, and remember our continue condition is that we're going to keep going so long as low is less than equal to high. Oh, sorry, there's a condition here. If there are no values, return empty string. I'm going to update our best to have empty string by default. And at the end, after the binary search, I'm going to return best 1, right? Which is going to be this thing. If you never find a value, then we'll just return empty string. Otherwise, best is going to be updated, and then we'll return the appropriate value. All right, let's do binary search things. Calculate the mid, and after that we need a check. Is the timestamp at mid less than equal to this timestamp in our argument? Well, if it is, then it's a valid candidate, right? So this is going to be the valid candidate branch, and the else is going to be what we do if it's not a valid candidate. If the timestamp is greater than what we have in best, then we're going to update our best to the tuple at mid, and then we're going to get greedy and see if we can find a better answer. And in the else clause, it means that we didn't find a valid candidate and we need to look for a smaller timestamp. So we're going to reduce high to mid -1. And there you go. That's the code. Let's talk about time complexity. So the initialization is just going to be an O of 1. And for the set function, when we do this hash map key, we know that a hash map lookup is a O of 1 operation, and appending a value to the end of the list is also an O of 1 operation. So set is going to be O of 1. And then what about the get function itself? Hashmap access, again, is O1. This is an O1 operation, more O1 operations. And the big one is going to be this loop, which is going to execute log n times, where n is the size of the list associated with the key, right? And that is multiplied by the cost of running each iteration. But all of these operations are O of 1, so it will be log of n times 1, which is just log of n. And so for the space complexity, we have this hash map that we're keeping track of. The space complexity of holding all of these hash maps is going to be O of n. And for the other functions, we just have local variables that are O of 1. And R here is holding a list, but this is actually just a reference to the list that exists in the hash map. So I would say that this is not extra space. The big one really is just a hash map. And that's about it. Thanks for watching. Okay, bye.